All right, so the definite integral, like I said before, the definite integral is a way of finding the area under the curve without having to make a lot of geometric areas. So in the previous section, we looked at the area under the curve by using a finite number of rectangles and trapezoids. Now we're going to use a set of steps to find even more intimate or tiny Riemann sums. So I think these directions were on the page before for you, so that you could just look through the Riemann sum directions. So I gave you, I think they're actually like even before your homework, so you had all the steps to go through. But I just wanted to quickly like walk through them in case anybody was still confused. You have to make your delta x, which is b minus a all over n. After that, and you have your subintervals, you pick the numbers on them. If it's a left, you pick the left. If it's a right, you pick the right. If it's middle, you pick the midpoint. And then we use the width and that height to multiply and get the area. And then you find the sums of all those products. So that is what a Riemann sum is. And those are the steps we used to find it. So again, just to reiterate the importance of a Riemann sum, following the steps on that slide, a Riemann sum is the sum of all those tiny rectangles added together, where x sub I represents the point and f of x sub I represents the height at that point. So that leads us into what we're going to look at today. And what we're looking at today is the Riemann sum as a summation with a limit. So just like in calculus, we started derivatives with limits, we also start integrals with limits. So if f is our function defined on a closed interval AB, for any partition P of AB, we let the number x sub I be that chosen point. So you saw on the previous page, x sub I is just any point. It represents either the left, the right, or the middle of the rectangle we are looking at in particular. So this is the limit of the magnitude of P, meaning that it takes into account its direction and speed.
Is that what it's for?
Yes. As it approaches 0, this symbol right here, it looks kind of like an E. That is the Greek symbol for summation. So that means the sum of the values from I to infinity. So what that is doing is meaning that my subintervals, because n represents subintervals, is infinite. Yesterday, a lot of our subinterval values were 4, 6, 8. This summation is saying that there are an infinite number of rectangles. That n going to infinity tells me that we are looking at an infinite number of rectangles, making those rectangles really, 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 really tiny, because there are now an infinite number of them. So each rectangle is like the width of the thinnest thin you can think. And then in that summation formula, f of x sub I still represents the height of the rectangle at the ith value. And delta x sub I represents the widths of each of those rectangles. Anybody miss any of those explanations? Anything you still need? Because today is a lot of explaining. It's a lot of understanding. So it says what that equation means is that if we no longer care if our subintervals are the same width, and we saw yesterday some examples of Riemann sums where my subinterval widths were different, that notation for P allows us to denote that the longest subinterval length can be forced into a length of almost 0. That leads to the big conclusion. All continuous functions are integratable. All continuous functions are integratable. Just like in order to be differentiable, it had to be continuous. If it is continuous, it has an integral. What, honey?
What was our homework questions yesterday?
Just the 5.1 papers. It was like 1 through 8. Yeah, it was like the papers right before today's notes. That leads us into a definite integral. So those of you in physics, I know you already know what this looks like because I kind of walked you through one. But a definite integral is comprised of many parts. The integral symbol itself kind of looks like the letter S because it stands for sum. The integral symbol itself kind of looks like an S because it stands for sum. And then the upper and lower limits. The upper limit is going to be where you end. The lower limit is where we begin. F of x is referred to as the height, and it is also referred to as the integrand. F of x is known as the height, but it is also referred to as the integrand. dx represents the width. dx represents the width. And differential x is the variable of integration. So if it's dt, then t is the variable of integration. If it's x, x is the variable of integration. If it was a y, y would be the variable of integration. So the variable that follows the d is the variable of integration. The variable that follows the d is the variable of integration. The definite integral and the limit are related. The definite integral and the limit are related as follows. The definite integral is equal to that limit. The definite integral is equal to that limit. 1. It's okay. So today what we're going to do is use the area under the curve idea to form an integral from a to b and find the area under that curve, given the curve is an integral now instead of being given to us as a table in a Riemann sum. So we can define the area under the curve to be y equals f of x from a to b as an integral. And let's look at our first example of that. So for the example below, I want you to sketch the graph, shade the area we're trying to find, and then use that to find the geometric formula. So we're not quite at reverse power rule yet. So this integral in terms of a graph, if the function is 3, that represents the line y equals 3. It's from 2 to 9. So that means geometrically the integral from 2 to 9 of 3 dx is equal to 3 times 7, because the height of the function is 3, the width of the function is 7, therefore 21. The integral from 2 to 9 of 3 dx is equal to 21. The integral from 2 to 9 of 3 dx is equal to 21. The integral from -2 to 1, so my graph is -2 to +1. For the absolute value of x, the absolute value of x is a v with a slope of 1. So that means this point here is at 1, 1. -2 is at 2. -1 is at 1. So that means the area under these curves are represented by 2 triangles. So to find the area of that integral from -2 to 1, we're actually thinking of it as 2 integrals from -2 to 0 for the blue part, and 0 to 1 for the red part. So just like we could take limits and functions and break them into smaller parts, we can also take an integral and break it into smaller parts, as long as the new upper and the new lower bound match each other. So the only way I could take that limit or that integral and break it into 2 is if my upper and lower matched each other. So the blue plus the red. So the blue is represented by a triangle with height 2 and base 2. And the red is represented by a triangle with height 1 and base 1. So we get 2 plus a half, or 2.5. So the area under the curve, or the value of the integral, is equal to 2.5. The area under the curve, or the value of the integral, is equal to 2.5. A square root involving a number and a x squared will represent a semicircle. This represents a circle of radius 3 because it's r squared minus x squared equals y. So we have a semicircle of radius 3. So the area under this curve is represented by the area of a half circle. So it's 1/2 pi r squared. Because the area of a circle is pi r squared, but half of it represents a semicircle. The radius is 9. So this is 1/2 pi 9 squared, or 9 pi halves. So the value of the integral is 9 pi halves. We have 3 minus x from 4 to 8. So that makes my y-intercept 3. I have a slope of -1. My x-intercept will be +3 then for that reason. Because 3 minus 3, 0. So 4 would be at -1. 5 at -2, 6 at -3, 7 at -4, and 8 at -5. So we're looking for the area, and now my area is a trapezoid. So there's 2 ways to do this. It says consider the function and find the area. What do we know about area in geometry? Area has to be what? Positive, yeah. So the integral and the area, in the case of this example, are not going to be equivalent. The integral and the area are not equivalent. Because area is positive and an integral can be negative. So the integral from 4 to 8 of 3 minus x dx would be equal to 1/2. Now the height of the trapezoid is the length on the x-axis. So that's 1, 2, 3, 4, because it's from 4 to 8. The bases are the units we're going down, so -1 and -5. And that's where I was saying that the integral can be negative, where the area has to be the absolute value of those problems. So half of 4 is 2, and then that's times -6. So the integral value, because the function is below the x-axis, is negative. The integral value, because the function is below the x-axis, is negative. The area is positive because area cannot be negative. So the area is the positive integral value. In this case, the area does not equal the integral because the value of the function falls below the x-axis. Area should remind you of speed. Area should remind you of speed. So velocity is kind of like the integral value. Speed is kind of like the area value. Speed is never negative. Area is never negative. Okay, I already did the now let's evaluate part. So, area, like I just said, is inherently positive. So if you didn't get that from my last example, this is just a way of showing you how the integral and the Riemann sum can all be kind of different. Here's different examples. So the blue Riemann sum is like the worst summation. The yellow is the best because it has the most. So area is inherently positive. However, a Riemann sum or an integral can be negative if the rectangles lie below the x-axis. Therefore, an integral can have negative values if the curve lies below the x-axis. So we're expanding upon our knowledge and skills, and we're now looking at values that can take on negatives. So we have to take into account the shape, location, and kind of values of a graph. For the next example, we're pretty much going to be taking into account one value and using it to find a whole bunch of others. So we're given that the integral of the function y equals the sine of x is equal to 2 from 0 to pi. So let's imagine what that's saying. I ran out of room. That was such a good curve. Not as perfect as it could be, but we know that the sine curve itself goes from 0, 0 to 0 pi, or rather pi 0, and then to 2 pi 0. We know that it begins above, so this is at pi halves, comma 1. And then it goes down below, so 3 pi halves, comma -1. The range of sine is 1 to 1, and one cycle occurs from 0 to pi. We are given in the directional statement that the sine of x from 0 to pi, so that's 0 to pi, sine of x dx is equal to 2. That's what that statement gives us. It says, given that the integral of this function is equal to 2 from 0 to pi, let's find the following integrals. So if the area from 0 to pi is equal to 2, and the area of the sine graph below the x-axis is a direct reflection of what's above the x-axis from 0 to pi, the integral from pi to 2 pi of sine x would then be equal to -2, because this area is below, therefore it takes on a negative value. So therefore, the integral from 0 to 2 pi would be the sum of the area. So remember I told you that you could rewrite an integral. So it's kind of like 0 to pi plus pi to 2 pi, which we both know both of them now. So that's kind of like saying 2 plus -2, which means the value of my integral from 0 to 2 pi is 0. Now we want to know 0 to pi halves. Well, pi halves represents the midpoint of a circle with area 2. So now we're talking about a fourth of a whole circle, or half of my semicircle. So half the area of 2 would become 1.
Did you skip over one?
I don't believe so.
We had 0 to 2 pi.
I already did 0 to 2 pi.
Oh yeah, you did.
Okay. And if we go the opposite direction, so if 0 to pi is +2 and pi to 2 pi is -2, if that sine graph went this direction, mini eraser. This would repeat that -2 pattern. So negative pi to 0 of sine of x dx is also -2. So once again, -2 plus +2 would be 0. Just like limits, integrals can be broken into multiple parts. So the integral from 0 to pi of sine x dx plus the integral of sine x, well, that would represent a function shifted 2 units up. So you would have to take the graph of sine x and shift it up 2 units. So that makes y equals 2 kind of like my new x-axis. So my curve now goes from 0 to 0 to pi 2. So it goes up from 0 to 0 to 0, 2, and it goes up from pi to 2 as well, or from 0 on pi to 2 as well. We're still given the statement that this area here is 2. But now to get from the sine curve to the x-axis, I have this added rectangle below. So I need to find the area of that rectangle and add it to the area that we already know for my sine. So that rectangle has a width of 2. Sorry, not a width of 2, a height of 2 and a width of pi. It has a height of 2 because it got shifted up 2 units, and we're reaching from 0 to pi, therefore its base is pi. So the area of the rectangle is 2 pi. The area of the top semicircle is 2. So the area of the integral, or the value of the integrand, is 2 plus 2 pi. Okay, so what I want to do, that's sort of our summary of the first part. You're going to take your 4-minute break. We're going to look at calculator stuff. And then we're going to come back and we'll have time to work on a bunch of problem sets and go over a whole bunch of problems. So go ahead, take your break. I'm going to rewrite all those problems, don't worry about it. Take your break, breathe for a few minutes, stretch it out. That was a great 30 minutes. Functions for this are a great way to check your answers. But as you know, a majority of my tests, the majority of the AP tests, and in some college classes, no calculators are allowed at all. So we don't spend a lot of time in here using calculators, but this is one instant where I think it's really helpful to kind of see what's happening with the area under the curve and an integral on a calculator. So let's take, for example, that first value. It's x squared minus 2x plus 2. And we are evaluating from 1 to 3. So I'm going to fix my y window and my x windows to kind of get a little bit closer in on that. So I'm going to make my x from 0 to 5. So 1 to 3 is included in showing. And then I'm going to make my y values. So I just know quickly plugging in 2, the y-intercept, plugging in 0, the y-intercept is 2. So I'm going to make my y min 0 and my y max 20. Hoping that my graph fits in that window. And if not, I could always adjust. So there is my curve. It almost fit perfectly. And we want to find the area under the curve. So an integral represents the area under the curve between the x-axis. So that's why I could make the y value 0. And I'm going to actually just make it -1. You don't have to change yours at all. just so you can actually see that when we do the integral, it doesn't go below the x-axis. And then in our classes in the past, we've hit this button right here for trace. We're going to hit second and trace again. And what I want you to notice is that the options for 6 and 7 are actually calc options. 6 would represent the derivative, because it's dy dx, derivative of y, with respect to x. So if you wanted to know a derivative value from a graph, you could do option 6. So let's say I wanted to know what the derivative was at 4. The derivative of this function at 4 is 10. So the derivative of that function at 4 is 10. Or it's 6. Your coordinate point is 410. Sorry, it's 6. It's whatever that dy dx equals. We could do this again for second trace. Go to option 7 for the integral, and we call them the lower and the upper limits. So the lower limit in this case is 1. So you type in 1 and hit enter. The upper limit is 3. So we type in 3 and hit enter. And what your calculator is going to do is find the area from 1 to 3 under the curve, between the curve and the x-axis. So it's going to find the area under the curve, between the curve and the x-axis. If you get a decimal like 0.666 repeating, we know that that's really 2/3. So this area would be 4 2/3, or 4.6, and just make sure you put the repeating bar above it. So I'm going to say on my calculator screen, you just need to make sure you fill that in on your notes, because I'm not going to go back and forth. I also want to show you how you could do this with not graphing it. So hit second quit, go to your home page. You're going to hit the feature on your calculator that says math. So right here, that feature says math. You're going to go down to option 9. That stands for function integration. You're going to hit enter. And on your calculator, you should see an integral looking screen. You're going to type 1 for the lower, 3 for the upper. You type the function in here, so it's x squared minus 2x plus 2. And then after the d is the x, because we're taking the derivative of this function with respect to variable x. And once again, we see that it gives me a value of 4.666. You could hit math, enter, enter, and it would turn that into a fraction. Let's say this was a problem on the AP exam, and I had to do something in the graph and something on the home screen. You can go to y equals. So let's look at example 6 now. This one would be a little bit trickier to do in y equals, because you can't really adjust for everything the same way graphically. So I'll wait to do the y equals thing until number 7. So for number 6, you're going to type in the 3 first, then the plus 2. Now you're going to hit math 9. Type in your integral from 0 to pi thirds of tan. And the one thing you need to do or make sure of is, since this is a trig function with radians, you need to make sure the mode on your calculator is also in radians. If your mode's in degrees and I'm asking you to find an answer with radians, you're going to get the wrong answer. So we should get 4.3862. And again, on the day of the AP exam, I'll remind you to change it to radians. I might also have you turn your calculator out of float and onto 4 or 3. So what that would do with your answers is automatically give them with 3 decimals so that on your test you don't forget to write down 3 and or you don't stress about rounding to the third, etc. So everybody okay with everything I've sort of shown you on the calculator so far? So we already did sort of the graphing idea, but in 7, I list the directions for you. So in 7, we're going to type in the square root of x function for y1. I need to change my window because I ended it at x equals 5. Now it has to go out to 10. And I can actually zoom in because I know the square root of 9 is 3, so I know my y values don't have to really go out all that far. So I'm going to hit graph. I'm going to see my nice little square root of x function. And then if I want to see the area under the curve, I go to second trace, option 7, enter my lower, enter my upper, and I see that the value of the integral is 14.418. 14.418. What I was going to show you on the home screen is if I've entered the function into y1 and I want to repeat using that, you could go to math, option 9, put in your upper and lower bounds, and if the function was something long and crazy and you didn't want to retype it, you can hit the vars key and then you go over to yvars and select function, and anything or whatever you have in y1, it will retype that in y1 on your calculator. And then I just fill in my dx and hit enter. So if I already put something in y1, or if I want to use that 14.41, you can go down here and hit the option for store. It's going to put that answer with an arrow, and I could store that value in x. And then if I needed to use that 14.41 again, if I type 3x, it'll multiply 14.41 times 3. Or if I needed 3x squared minus 2x plus 5, anywhere you have an x, it's going to replace it with that 14.41 if you use that STO for store feature.
How do you get rid of that so it doesn't do
So the default is always something. Like the x value is always defaulted to 0.
it?
So like you can't, like if you just typed in x and your calculator was at like the reset mode, it would tell you 0. So like if you wanted it back to 0, you just hit 0 STO x. Oh, it didn't let me hit 0. And you could restore it with 0.
Okay.
But yeah, a lot of kids always think it just represents x. It actually always has a numerical value to it. All right, let's head back to our notes then. So I have a couple pages to skip because I went through these with you. And that leads to our first integration theorem. Our first theorem of integration says that all continuous functions are integratable. That's really nice because that's really easy to remember. So for example, if we were given this graph, and again, your graph is drawn, I had to accidentally erase mine. If you're given this graph, and we are told that A is equal to 3 and the area below is equal to 7, then from that we can come up with integrals to represent that. So what that means is that the integral for this first region here would be the integral from A to C of f of x dx, because you need the dx, is equal to 3. And sorry, I drew on the out. It'd be like that. The integral from C to B represents the area below that curve. Which is -7 since it's below. So this is asking me to find the area from A to B. So the area from A to B will be the area above minus the area below, because A to B of f of x dx would be equal to A to C of f of x dx plus C to B, so that I can get rid of the C kind of in the middle, so that it's really like A to B, which would be equal to +3 plus -7, or -4. So the value of the integral from A to B in terms of this given graph is -4. So again, that's a lot like the sine graphs that we were looking at. It's the area above, you subtract any areas below, and you get your total areas. Okay? Once again, we have -1 to +3. My y-intercept is -1. My slope is up 1 and over 2. So this integral is going to be like two triangles summed together, where you have a triangle below and a triangle above. So to find the value of the integral, you have to find the value of the two triangles, and you subtract the green one from the red one. So the green triangle would be 1/2. It's going from -1 to like 2. So that makes its height 3. And then the base comes down 1.5 units. So that's like down -3/2. So 1/2 times -3/2 is -9/4. The red triangle is 1/2, base 1, height 1/2. So it's +1/4. So the value of the integral is -9/4 plus 1/4, which is -8/4, or -2. And if you don't believe me, you could now type this in on your calculator and check your work. So that's kind of like the purpose of giving you that calculator trick, is that if you're actually like concerned or you're just unsure of yourself, you can now use the calculator to check your work that you're doing by hand. Okay. So the next example is pretty similar. So it's -3 to +3, a y-intercept of +3, apply my slope, so this time we have a trapezoid once again because it's a linear height. Here's my height. So the height of the trapezoid is 6. And then you'd have to find your coordinate values. So these coordinate points, this is really like plugging in -3 to my function and +3 to my function. So if you've been wondering where I got those values from, it was just me plugging them in to the function. So it was like -3/2 plus 3, and then it was +3/2 plus 3. So all I did was kind of plug them in to my function. So that become 1/2 the base, which is 6, and then the two little mini heights of 3/2 and 9/2. So you get 3. Here we get 12/2, which is 6. So 3 times 6 is 18. So a lot of geometry. This represents a circle shifted down 3 units. So instead of my circle sitting on the x-axis, my circle is going to sit on the y equals -3 axis. But our calculator finds the area between the curve and the x-axis. So the integral value is going to be this blue region right here. So this again is kind of like the geometry days. We're going to find the area of the entire blue rectangle, and then we have to subtract from it the area of the red circle. So to find the area of that blue region, we have to find the area of the rectangle. So that goes down 3 and across 4. So the area of the rectangle is -12. But I need to remove from it the area of that semicircle. So the area of a circle is 1/2 pi. The radius is 2 squared. So the area of the circle is 2 pi. So since this is below the graph, and we're getting rid of the red region, we're going to add that 2 pi to the negative area. So the value of the integral, and I want to write it at the integral because I like it to be consistent, would be negative 12, adding back the red region of a positive 2 pi. Because it would really be like minus a minus. You'd be subtracting the circle, but the circle's area is negative because it's below, so it turns to adding. You could kind of think of it, if the negatives are not as confusing, you could think of it as, okay, the rectangle minus the circle, but because we're below the x-axis, it's negative that value. So that negative would have distributed to the 12 and not making it positive. There you go. Yeah, I saw your face. I was like, okay, she doesn't get it. I got it. I'm good. You can, yeah, I can answer. And like I told Nick yesterday when he asked me a question I couldn't answer, I was like, I'll investigate. I was like, if I couldn't have answered you, I would have said the same thing, and then I'd get you an answer tomorrow. But that I did know. That pretty much sums up like the next few examples, except for the fact that we know in calculus, nice, pretty numbers isn't our thing. They like to speak in terms of general. So this represents 3 theta delta theta. This is a general thought. So 3 theta at 0, 0 would go through the y and x origins. It's got a slope of up 3. So it means it would go up 3 and over 1 as you continued through your process. A and B are general. You could put them anywhere you wanted on your graph. So I'm going to say that A is at my first tick mark and B is at my second tick mark. And on the previous screen, I told you that these values I was getting came from plugging them into the function. So f of A would be like 3 plugged in an A for your theta, so it's like 3A. And f of B would be like plugging in B to your theta, so that would be 3B. So this height here and that height here are 3A and 3B. So this is once again a trapezoid. It looks like a small subinterval of a Riemann sum. So the integral from A to B of f of 3 theta d theta is really equivalent to 1/2. The height would be B minus A. And then the bases would be 3A plus 3B. And that's why I was saying in calc, this is general. Usually we have numbers for B minus A or numbers for A and B. So that becomes, and I would FOIL these, 1/2 3AB minus 3A squared plus 3B squared minus 3AB. So it's nice as your plus and minus 3AB's cancel. So you'd get 3b squared minus 3a squared all over 2, distributing in your 1/2. And you could have wrote negative 3a squared. I just don't like a negative in the front. And last but not least, our very first line of the theorem is you can only evaluate an integral if it's continuous. 1 over x is not continuous at 0. Therefore, the integral does not exist. This is the case of DNE. So I just wanted to throw on one case where it is a DNE, a case of DNE.
But it only has to be continuous over that integral.
Correct. So like if the integral was, let's say, 2 to 4, now it is integratable.
Okay.
And I just thought for the heck of it, I'd give you guys some of like our old limits and reviews from chapter 2. But the main idea is it's not differentiable or integratable at x equals 0. It's not differentiable because it's a vertical asymptote. It's not integratable because you have discontinuity. And the only rule for integration is continuity. So we're going to do, I'm just going to tack on 2 other problems, and then the rest is 8 to 28 evens. So that's a case when you were looking earlier, I knew I was changing it. I took away problems, like some of the odds. So it's 5 and 6, and then 8 to 28 even. So it's only about 12 problems because I know today's lecture was a little long. And at the same time, just trying to make sure we get all of our content